Look at this simple two-dimensional grid. In 1970, a mathematician decided to see what would happen if he applied a few strict biological rules to it. Depending on how many neighbors a cell has, it will either live, die, or survive to the next generation. That's the entire premise of what became known as the game of life. But let those rules run across thousands of generations, and something incredible happens. The grid spontaneously generates moving objects, breeders, and systems so complex they are actually Turing-complete, meaning this simple grid of dots can run any calculation a modern computer can. When Scientific American published the rules, it became an absolute obsession. In early computer labs across the world, researchers were burning through millions of dollars in mainframe computing time just to watch these artificial life forms evolve. The architect behind this viral phenomenon was an English mathematician named John Horton Conway. He was charismatic, highly extroverted, and entirely frustrated by the attention. Conway grew to resent the game's popularity. To him, the grid of blinking dots was a triviality that eclipsed decades of work on the underlying architecture of symmetry and numbers. To understand his actual life's work, we have to look at how he spent his time at Cambridge University. Conway spent hours in the common room playing backgammon and inventing quirky, abstract puzzles. Conway applied absolute academic rigor to these pastimes, eventually formalizing the logic of play into a new discipline, combinatorial game theory. This branching tree diagram illustrates how that happened. By mapping out the abstract left and right choices in competitive games, he realized the win and lose states mapped perfectly to numerical values. This led to his invention of surreal numbers, an entirely independent number system capable of handling infinitely large and infinitely small values. Rigid traditional algebra had missed these numerical truths completely. Conway discovered them simply by taking the logic of play to its absolute limit. His ability to manipulate abstract systems wasn't limited to numbers. He possessed a unique cognitive spatial awareness that allowed him to mentally untangle complex, multidimensional geometry. Watch how this complex, tangled three-dimensional knot behaves. Mathematicians struggled to categorize shapes like this, until Conway developed a system for flattening and translating them into a clean string of algebraic notation, known today as the Conway knot polynomial. He applied this same visual intuition to Penrose tilings. These are infinitely expanding shapes that fit together perfectly without ever repeating their pattern. Conway systematically decoded their underlying mathematical properties. This notation system provided a precise mathematical language for decoding the architecture of space itself. His drive to categorize mathematical structures culminated in the Atlas of Finite Groups, a massive index mapping out the properties of complex symmetries. This structure is a multi-dimensional visualization called a Leach lattice. Conway analyzed how these multi-dimensional spheres pack together, and in the process discovered 3 brand new, highly symmetrical mathematical groups. Then, working with his colleagues, he noticed a bizarre numerical coincidence that seemed to link his finite groups with an entirely different area of mathematics. They formulated a theory so unbelievable, they named it monstrous moonshine. The conjecture proposed a direct bridge between the study of finite groups, the math of symmetrical shapes, and complex function theory. Decades later, theoretical physicists realized why that bridge existed. The monstrous moonshine conjecture became a critical component of string theory. Conway's abstract, playful symmetries were actually describing the physical rules that govern our universe. In his later years, holding the von Neumann chair at Princeton University, Conway continued to push at the boundaries of human knowledge. He eventually turned his attention to quantum mechanics, partnering with Simon Cochin to publish the free will theorem in 2004. When you observe a spinning subatomic particle, physics dictates a strict set of rules, but Conway's theorem proved a radical premise. If human experimenters have the free will to choose what they measure, then elementary particles must also be free to choose their spins to make those measurements consistent. The irony is sharp. The man who became famous for programming a strict, highly predictable set of biological rules for his game of life spent his twilight years mathematically proving the inherent unpredictability of actual reality. Conway never resented the game of life because he hated games. He resented it because he wanted the world to look past that single grid and see the entire board he was playing on. He viewed the universe as a joyous puzzle. He maintained a lifelong collaboration with puzzle master Martin Gardner, constantly sharing his research not as dense academic posturing, but as curiosities to be shared and solved. In April 2020, Conway passed away from complications related to COVID-19. His death marked the sudden end of a prolific, wildly inventive mathematical era. Through surreal numbers and untangled knots and the shape of the universe, his legacy proves that true genius requires a relentless, joyful pursuit of play.